going to take some notes on prime factorization. A lot of this should be review, so we just want to look at what work needs to be shown and that sort of thing. So first, let's review what it means to be a prime number versus a composite number. A prime number is a natural number. So that means it's a counting number. It's greater than 0. So when you started counting, when you first learned about numbers, you started with 1, 2, 3, and so on. So a natural number that has exactly 2 positive factors: itself and 1. And then we have a composite number is a number with more than 2 positive factors. So then you start looking at numbers that you've heard are special or unique or that sort of thing. So negative numbers don't fall into either category because they're not natural numbers. Same with 0. 0 is not a prime number or a composite number because it's not a counting number. And then when you look at the number 1, the number 1 only has one factor, just itself, the number 1. So it's not prime or composite either. The very first prime number we have is 2. The number 2 has 2 prime factors, two positive factors rather, 1 and itself, 1 and 2. And then 3 is the next prime number, and then 4 is a composite number. Every even number is going to be a composite number because 2 is one of its factors. And you go on from there. So if you're checking a larger number to figure out if it's prime or composite, you should check numbers in order to see if things go into it evenly. See if you have any other factors. So if you're checking in order, you only have to check the prime factors. You don't have to check 4 because 2 would have already gone into it. You don't have to check, say, 12 because 2 would have gone into it and 3 have gone into it. So you only have to check prime factors to see if a number has anything else that goes into it. You can use the divisibility rules. For checking 2, 3, and 5. So divisibility rules are fine to check, but then you don't just stop at 2, 3, and 5 and say, nope, it must be prime. You might have to use division. So else you need to try to divide to check for other prime factors. So here's an example of what you might be asked for a task and what work you need to show. It says, tell if each number is prime or composite. So when I look at the number 147, a lot of people say, oh, it ends in 7, I think it's going to be prime. But my divisibility rule for 2, it ends in a 7, so it's definitely not even. It's not, doesn't have 2 as a factor. But the 3's divisibility rule, I would add up 1 plus 4 plus 7, and I would get 12. 12 is a factor of is a multiple of 3 rather, so this is composite. 3 goes into it evenly. It's divisible by 3. Some people do then find out what the other factor is that goes with the 3, and that's fine if you need to find the factors, but just showing that 1 plus 4 plus 7 is 12 is enough to know that 3 goes into it. 3 is one of its factors. Now when you get to 157, a lot of people again want to automatically jump to prime. And you got a 50-50 chance of getting it right, so that's why you have to show your work. So here I would say 2 doesn't go into it evenly because it ends in a 7. 3, I would do 1 plus 5 plus 7, that's 13. 3 doesn't go into it evenly. 5 doesn't go into it evenly, but now I have to actually do some division to check other prime numbers. I don't have to check 6, 2 and or 3 would have gone into it already, but I do have to check 7. Try to divide 7 into 157. Let's see, the 2 goes into 15 twice, that's 14. I subtract, get 1, bring down the 7. 2, that's 14, is going to have a remainder, so that doesn't work. I don't have to check 8. I don't have to check 9. I don't have to check 10, but I do have to check 11. 11 goes into the 15 once, that's 11, that's 47. That goes in 4 times, 44, it's going to have a remainder of 3, so it still doesn't work out. I do need to keep going just a little bit longer, and I'm going to show you when you know to stop. I don't have to check 12, but I'll check 13 into 157. 13 goes into 15 once, that's 13. You subtract, we get 2, we bring down, we get 7. 13 goes into 27 twice, but then it will have a remainder 1. So that doesn't work. But notice, 13 times 12 is what's going to get us really close to the 157. If I check my next prime number, it's going to have to multiply with something smaller than 12. But according to my logic, by doing things very orderly, in an order, not skipping anything unless I know it's because it's composite, I know if I have a number times something smaller than 12 gets me 157, I would have found that number that's smaller than 12. So when my quotient over here is smaller than what I'm testing out, the 13, then I know I can stop, and I know that this is prime. And then for the next section of our notes, we're going to be doing prime factorization. You need to know if a number is prime or composite to be able to properly do prime factorization. A lot of people, when they first see the term prime factorization, they're like, it sounds familiar, not really sure, and then I say factor trees, and they go, oh yeah, that. So one of the ways to find prime factorization is with factor trees. So let me clear the ink from the top section so we can focus on the prime factorization section. What I'm going to show you in the notes is that you don't have to do factor trees, but it is one very common method that will get us the prime factors, and it will, some people just like it. It's fun to just break it up little bits at a time. So let's see. You can find the prime factorization of a number by using a factor tree. But do not forget the final step of writing the multiplication expression. With all the prime factors in order. And you might be asked to use exponents, or you might choose to use exponents. But here's a little tip in that box. Circle the primes or bring them all the way down to the lowest level of branches, because there are some people that lose their prime factors way up at the top of the tree. And then when they write their prime factorization, they don't get it accurate because they're missing some. So let's take the number 45. If we're going to break up 45, some people might immediately go, okay, 9 times 5. And that's great, that's fine, you can do that. And then the 9 still has to be broken up because it's a composite number. You have to break it up all the way till it gets to its prime factors. When that 5 did not need to go to the next level, some people might circle it to be like, don't forget about it, even if I end up going way, way down many levels below. And so they might do that. Now someone else might take that 45 and break it up into 3 times 15. The 3 is prime, but the 15 is not. So they might bring the 3 down to that next level and break that 15 into 3 and 5. Also, some people, not everybody, and it's not required, write the multiplication part within their tree, and that's all fine and dandy. But no matter which method of making the tree, if that's your choice is to make the tree, you do have to make sure your final answer is 45 equals 3 times 3 times 5, or 3 squared times 5. And my 2's not matching up. And you know I'm going to have to rewrite that. So 45 equals 3 times 3 times 5. Or if my directions said I had to use exponents, 3 squared times 5 would be a final answer. You can also use what's called an inverted tree. So it looks kind of like division, breaking out prime factors as you go through it. So if we had, say, 70, let's switch up the coloring here. If we had 70, you could divide out whatever you happen to see first as a prime factor, so 5 maybe, and you have 14 left. And then you can divide a 2 out of that, and you have 7 left. Oops, you don't close up your tree down the bottom. Because 7 doesn't need to be broken up anymore. Other people might take that 70 and they might say, okay, it's even. I see that nice and quick, and I have 35 left in there. So I quickly saw that 2 could be divided out. If 35 left, 35 is not prime. Now I'm going to take that and divide the 5 out, and I'll have 7 left. Other people take the 70, divide out the 7. They have 10 left. 10 is not prime, so they divide out, say, a 2 and get a 5. But again, no matter which method you use, at the end, put your prime factors in order. It's 2 times 5 times 7. Now those of you who don't like to show your work and or you don't like to take up the space on the paper, you could just divide out the primes in your head, but you have to start with the smallest one to make sure that you don't miss anything. So another option is to divide out the primes by starting with the smallest primes as many times as necessary, then the next smallest prime, etc. So if I have 30, I can say, okay, I can take a 2 out of that. That's my smallest prime. And in my head, I say I have 15 left. Let me make some room for my thought bubbles. So 30 equals 2 times, and I'm like, okay, I have 15 left still, and now I have to break that up. I can take a 3 out of that. I can't take a 2, so I always start with my smallest. I can't take another 2, but I can take a 3 out of that. Times, now I have 5 left. So 2 times 3 times 5. So if the numbers are simple enough, I could go ahead and just break it out that way. And you don't have to show those thought bubbles. That's just what would be in my head. And then the last thing to keep in mind is sometimes you need long division. To find a number's prime factors. So if I have something like 2,475, I cannot simply go, oh, it's 5 times, I don't know what goes with it. I know 5 is one of its factors because, or one of its prime factors even, because it ends in a 5. My divisibility rules help with that. But then I need to do long division to find out what goes along with it. So I got 4 here, and that's 20, and that's 4, bring down the 7, now I've got 9, it's 45, 2 left, bring down the 5, and now I got 5. 495. Ugh. 495 is definitely not prime because I can take a 5 out of that. I don't want to lose this 5 when I'm doing my work, so I'm going to do that. Circle that 5 that was left behind there, and I'm going to divide 5 out of 495. Goes in 9, that's 45, that's 4, bring down the 5, that goes in 9. And I get 99. Another side, because 99 is not prime. But that 5 is, I don't want to lose it. I'm going to break the 99 into 9 and 11. Didn't need long division for that. 11's prime, so I'll circle that, but the 9 gets broken up into 3 and 3. Those are my primes. So now I know that 2,475 equals 3 squared times 5 squared times 11. Don't like the way it looks because it's all squished in. But you have more space on your paper than I do. I'm going to fit it all on one screen here. Got the 5 here. So again, 2,475 equals 3 squared times 5 squared times 11. So the big points is prime or composite, it's not just a guess. You actually have to show some work. If you're going to use a factor tree, don't lose any of your primes way up high, and also you might need to use long division, but you don't have to use a factor tree. You could use inverted division, or you could just carefully, systematically divide out the primes. So that's what we have for our notes for today.